China just built the world's largest train station on top of a mountain. Picture 170 football fields of steel, glass, and concrete, 5 times the size of Grand Central Terminal, anchored into a seismically active mountainside, completed in 38 months. You heard that right. And the size is not even the real story. The real story is how they built it, and why nothing like it has ever been attempted before. Before a single beam went up, engineers had to face the one thing standing between them and that record, the mountain itself. The mountain that said no. Most train stations are built where it makes sense to build them. Flat land, stable ground, bedrock close to the surface. You pick a site, you pour the foundations, and you work upward from there. That is how it has always been done. Chongqing does not care how it has always been done. This city sits on a peninsula of mountains at the junction of 2 of China's mightiest rivers. It rises and falls so dramatically that the roads don't just go left and right. They go over, under, through, and sometimes straight into the rock itself. Locals joke that the city exists in 8 dimensions. They are not entirely wrong. Now here is the part that most people never think about. When China decided to build the world's largest train station here, they didn't choose the flat part. There wasn't one. The site they selected sits on steep hillside terrain in an active seismic zone, a mountain face where the ground level changes so dramatically from one end of the station footprint to the other that if you stood at the low point, looked across to the high point, you would be looking up the height of a 4-story building. That elevation difference, spread across a footprint the size of 170 football fields, is not just an aesthetic problem. It is a structural catastrophe waiting to happen. Think of it like placing a dining table on a staircase. You can shim the legs, you can prop one side up, but the moment you load that table with any serious weight, every imperfection in the surface beneath it becomes a force problem. Now imagine that table weighs the equivalent of 2 million cubic meters of concrete and 366,000 tons of steel. That is what the engineers were dealing with. And the slope was only one part of it. The soil conditions across the site varied so dramatically that no single foundation solution could work across the entire build area. What held firm in the eastern section turned to something closer to compressed clay in the west. Bedrock sat at different depths, in different zones, sometimes shallow and reachable, sometimes buried so far below the surface that reaching it required an entirely different structural approach altogether. Engineers were not solving one foundation problem. They were solving dozens of them, simultaneously, on a live mountainside, in a seismic zone where the ground itself could not be fully trusted. Here is the detail that puts everything into perspective. The combined dead load of this structure, just the weight of the building itself, before a single train or passenger would have pushed conventional foundation engineering to its limits on flat ground. On a mountain, with inconsistent geology beneath it, that same load became a first principles problem. There was no existing playbook, no comparable project to reference. No engineering literature that said, here is what you do when the terrain fights you this hard. So they wrote their own. But designing a solution on paper is one thing. Convincing anyone to actually sign their name to it, that is where the real battle began. The blueprint nobody believed. Every great engineering project has a moment where someone has to stand in a room, unroll a set of drawings, and say, this is what we are going to build. And everyone else in the room has to decide whether they believe it. For the Chongqing East Station, that moment happened twice, because the first time, nobody did. The initial design proposal was rejected, not because the numbers were wrong, not because the engineering was sloppy. It was rejected because the ambition was considered categorically unreasonable. The plan called for a single unified structure, one continuous building spanning a mountain face across varying elevations, threading 4 metro lines, multiple high-speed rail platforms, conventional rail tracks, a bus interchange, and a direct airport connection through the same footprint, not adjacent to each other, not stacked in a rough approximation. Precisely integrated, 3-dimensionally, inside a single mountainside structure. The review committee sent it back. Here is what most people get wrong about Chinese megaprojects. The assumption is that scale alone makes them possible, that you simply throw enough money and workers at a problem until it yields. But the Chongqing East Station was not a brute force problem. It was a precision problem, and the design team knew it. So when the first proposal came back rejected, they did not scale it down. They went deeper into the engineering. The second proposal was more detailed, more technically demanding, and even more ambitious than the first. Picture a three-dimensional jigsaw puzzle. Not the flat kind you spread across a kitchen table, but one where every piece sits at a different height, connects to pieces moving in different directions, and has to bear a different share of the load depending on exactly where it sits in the overall structure. That is what the integration drawing looked like. 29 tracks, 15 platforms, 4 metro lines intersecting at different levels, bus bays, taxi drop-offs, an airport rail link. All of it threaded through a mountain face without any one system compromising the structural integrity of any other. The second proposal was approved. But approval was not the same as belief. The engineers who signed their names to it understood something the review committee may not have fully absorbed. They were not just designing a building. They were designing a construction methodology, because no existing method could build what they were proposing. The sequence in which you assemble a structure, this complex, on terrain, this uncooperative, does not follow standard practice. Get the sequence wrong, and the loads distribute incorrectly. Get the loads wrong, and the mountain wins. Now here's the brutal catch. The approved timeline gave them 38 months. 38 months for a structure that would take most countries 15 years to permit, let alone build. That is roughly the time it takes to design a mid-sized airport terminal in Western Europe, not build one, design one. So before ground was even broken, the engineers faced a question that had no comfortable answer. If the only way to hit that deadline was to run foundation work, structural steel erection, and roof installation all at the same time, on different elevation zones of the same mountain, how do you stop one work stream from destroying the progress of another? The answer required them to rethink construction itself. And it started not at the top of the mountain, not at the bottom. It started from the inside, moving the mountain from the inside out. Here is something that will reframe everything you think you know about construction. When you build a skyscraper, you dig down, you pour foundations, and you build up, layer by layer. The sequence is logical. The ground is your starting point and your anchor. The Chongqing East Station was not built that way. It was built from the inside out. The decision to begin excavation from within the mountain rather than from the surface was not a stylistic choice. It was a structural necessity. The terrain made conventional top-down construction almost impossible across significant portions of the site. The slope angles were too severe, the soil variability too extreme, and the seismic risk too real to allow the kind of open excavation that flat-ground construction takes for granted. So the engineers went in through the rock face itself, carving out the space the station would eventually occupy before the station existed to occupy it. Think of it like hollowing out a loaf of bread from the end, rather than slicing from the top. You are not removing the crust first. You are creating the internal cavity, while the outer structure remains intact, using the surrounding material as temporary support while you work inside it. That surrounding material, in this case, was a mountain. The excavation volumes involved are difficult to hold in your head. The team moved enough rock and earth to fill roughly 800 Olympic swimming pools. You heard that right, 800. All of it extracted from a seismically active hillside, through access points carefully engineered so that the act of removing material did not destabilize the very ground they needed to build on. Now, here's the part that blows people's minds. While excavation was happening inside the mountain, foundation work was simultaneously underway on the surface. This was not a sequential project. It was a parallel one. Different elevation zones of the site were at completely different stages of construction at the same time, some areas still being carved out, while others were already receiving structural steel. The site was not one construction project. It was closer to 6, running concurrently, on the same mountain, managed as a single integrated system. This is where the digital twin became not just useful, but essential. Think of it like a flight simulator running at the same time as the actual flight. A live, real-time replica of the entire structure. updating continuously as the physical build progressed. Every sensor reading, every structural measurement, every load calculation fed back into the model. If a stress concentration appeared somewhere in the data, a point where forces were distributing differently than the design predicted, you could see it in the twin before it became a crisis in the mountain. Before concrete set wrong, before steel bore a load, it was not rated for. On a project where 6 work streams are running simultaneously across a seismically active site, that capability is not a luxury. It is the difference between catching a problem at the design stage and discovering it when something moves. Here is what makes this incredibly exciting. The digital twin was not just a monitoring tool, it was a design tool. Adjustments made to the model in response to real-world conditions fed back into the construction drawings in real time. The building was being redesigned continuously as it was being built. Not because the original design was wrong, but because a mountain is not a controlled environment and no engineering model survives contact with geology entirely intact. The foundation system that emerged from this process was unlike anything built at this scale before. Because the bedrock sat at different depths across the site, the foundation piles varied dramatically in length from one zone to the next. Some were relatively shallow. Others went deep enough that the drilling equipment had to be specially configured just to reach them. And all of them had to work together as a single load-bearing system, transferring the combined dead weight of the entire structure into a mountain that sloped, shifted, and answered to no engineering standard written for flat ground. Getting that foundation system right was the project's first great achievement, but it was also, in a sense, the invisible one. Nobody photographs a foundation. Nobody makes a documentary about bedrock depth variations. But here is the thing. As extraordinary as all of that was, it is still not the main event, because securing the ground was only half the problem. Someone now had to put the people in place to build everything above it, and the scale of that human operation is the part of this story most people are completely unprepared for. The human machine. At peak construction, 40,000 workers were on this site simultaneously. 40,000. That is larger than most towns in England, larger than the entire population of Monaco. All of them concentrated on a single mountainside in Chongqing, working in rotating shifts so that construction never stopped, not at midnight, not in the rain, not during the humidity of a Chongqing summer, where the air sits so thick and hot, it feels less like weather and more like an obstacle. To run 6 parallel work streams on a seismically active mountain, you do not just need engineers and steel. You need a logistics operation that would embarrass most small governments. Think of the site not as a construction project, but as a city. A temporary city built for the sole purpose of building a permanent one. It needed roads, not just access roads, but internal road networks capable of moving construction equipment between elevation zones without disrupting the work streams already in progress at each level. It needed power infrastructure because the excavation equipment, the drilling rigs, the cranes, and the digital twin server infrastructure all drew from the same supply, simultaneously, around the clock. It needed accommodation because 40,000 workers cannot commute to a mountain every day from across a city the size of Chongqing and arrive ready to perform precision engineering. Now here is the part nobody talks about. Feeding 40,000 people 3 times a day, every day for 38 months is itself a supply chain problem of serious complexity. The site consumed enough food daily to stock a mid-sized supermarket from scratch every 24 hours. Medical facilities had to be maintained on site because when you are drilling into seismically active rock and erecting structural steel at multiple elevations simultaneously, injuries are not a possibility to plan for. They are a certainty to manage. But here is what made the human element of this project genuinely different from a Western construction model. The workforce was not just large, it was structured. Picture an army organized by skill, not rank. At the base, general labor, thousands of workers handling material movement, concrete pouring, site preparation. Above them, specialist teams locked onto specific technical domains, foundation drilling in one zone, structural steel connection in another, mechanical and electrical systems threading through a third. Above them, the engineering oversight layer, monitoring the digital twin, cross-referencing real-world measurements against the model, making the micro-adjustments that kept 6 simultaneous workstreams from tearing each other apart. Here is the detail that puts everything into perspective. Coordinating 40,000 people across 6 concurrent workstreams on terrain, this complicated required a command structure more similar to a military operation than a conventional construction site. Work packages were broken down to the day, sometimes to the hour. A delay in one elevation zone had knock-on consequences for the zones above and below it. Because the load sequencing, the precise order in which structural weight was introduced to different parts of the foundation system, was not flexible. You could not simply pause one work stream and let another run ahead. The mountain would not allow it. This is where the scale of the Chinese construction industry becomes something more than just an impressive number. 40,000 workers who understand their role in a tiered specialization system, trained within an industry that has spent 30 years building infrastructure at a pace no other country has matched, are not interchangeable with 40,000 workers assembled from scratch. The institutional knowledge embedded in that workforce, the collective muscle memory of a construction culture that has built more rail infrastructure in the last 2 decades than the rest of the world combined, was itself a structural asset. Without it, 38 months was not a tight deadline. It was a fantasy. But then came the moment no workforce, no matter how experienced, could prevent. Roughly halfway through construction, the mountain stopped cooperating entirely. When physics fights back. Halfway through construction, the mountain moved. Not dramatically, not in the way that makes headlines. It moved the way geology always moves, quietly, incrementally, and with complete indifference to the schedule of the 40,000 people working inside it. Ground shifted in the western foundation zone. Water began intruding through rock faces that the survey data had flagged as stable, and a load distribution calculation in one of the critical transfer structure nodes came back wrong. Not catastrophically wrong, but wrong enough that if it went unaddressed, the consequences would compound over time into something that could not be quietly corrected. Here is what the transfer structure actually is, because this is where the real danger was hiding. The mountain face drops by the height of a 4-story building across the station footprint. There is no natural level ground anywhere beneath it. So engineers designed a vast internal bridging system, the transfer structure that takes the combined weight of everything above it and redistributes it horizontally across the slope before driving it down into foundation. Piles at varying depths below. Think of it as the skeleton that turns a mountainside into a floor. Every platform, every track, every passenger concourse in the entire station sits on top of it. It is, in structural terms, the single most load-critical element in the building, which made the news that its calculations had come back wrong in 3 separate sections simultaneously, the closest this project ever came to a genuine crisis. Here is what makes this incredibly important to understand. On a flat ground project, a mid-construction ground shift is serious. On a mountain, with 6 concurrent work streams, it is a cascade problem, because every elevation zone is structurally dependent on the zones below it. A foundation adjustment in the west does not stay in the west. It ripples upward through the load path into the transfer structure, into the steel frame above it, and eventually into the roof system that had not yet been installed but was already being fabricated off-site. And every hour that deviation went unaddressed, it was compounding silently through every structure above it. This is exactly the scenario the digital twin was built for. The real-time model caught the stress deviation before it became visible in the physical structure. Engineers pulled the affected work packages, recalculated the load paths, and redesigned 3 sections of the transfer structure while construction continued in the unaffected zones around them. The parallel workstream model, the same feature that made the timeline so aggressive, was now the thing that saved it, because while the west zone was being corrected, the east zone kept moving. The mountain had pushed back. The engineers had absorbed it, adapted, and continued. But absorbing a ground shift mid-construction is one thing. What came next was the moment the entire project had been building toward. and the engineering challenge that had no precedent anywhere on Earth. The roof at the top of the world. 16,500 tons of curved steel suspended above a mountain, and not a single conventional crane configuration on Earth could put it there. 16,500 tons. That is heavier than 2.5 Eiffel Towers. You heard that right. The roof was not just large, it was curved, a sweeping architectural form designed to follow the natural contour of the mountain behind it. That curve, which looks effortless in photographs, is the reason conventional cranes could not be used. Standard crane operation assumes a relatively level base and a clear vertical lift path. The terrain at Chongqing East offered neither. The angles were too severe, the ground too uneven. A conventional lift would have introduced lateral forces into a structure already managing the load complexities of a mountainside foundation system. The margin for error was essentially zero. So the engineers designed a bespoke lifting system specifically for this roof, on this mountain, for this one installation. Here is the detail most people miss. The roof was not lifted as a single piece. It was assembled in large prefabricated sections off-site, transported up the mountain, and then connected and raised using a custom hydraulic synchronized lifting system. Dozens of hydraulic jacks working in precise coordination, raising the structure millimeter by millimeter. With the digital twin monitoring stress distribution across every weld and connection point in real time throughout the lift. The entire operation had to be sequenced around wind conditions. At the elevation of the site, a weather window narrow enough to ground helicopters was wide enough to compromise a 16,000-ton lift. They got it up, on schedule, on the first attempt. And when the roof locked into position above the completed platform level, above the threading of 29 tracks and 4 metro lines and 15 platforms, and a mountain that had spent 3 years trying to stop this from happening, the structure was complete. Which means it was time to compare it to the building it had just made. Looked small. What China just proved to the rest of the world. Give Grand Central Terminal the respect it deserves. When it opened in 1913, it was the greatest train station on Earth. 3 million square feet of Beaux-Arts precision, built on the bedrock of Manhattan, engineered to a standard that the entire world stopped to admire. It took 10 years to build. It has never been surpassed in over a century. That is not a failure of American ambition. That is a monument to how hard it is to build something truly unrepeatable. China just built something 5 times its size, on a mountain, in 38 months. 170 football fields of operational station, 29 tracks, 15 platforms, 4 metro lines, a direct airport connection, 2 million cubic meters of concrete, 366,000 tons of steel, a 16,500-ton roof installed by a lifting system that had to be invented because nothing existing could do the job. All of it anchored into a seismically active mountainside, where the ground shifted mid-construction and the engineers absorbed it without losing a single day on the critical path. The station opened in June 2025, on schedule. Here is what that actually means. This is not a story about one building. It is a story about what becomes possible when a country spends 30 years building the institutional knowledge, the construction culture, the digital infrastructure, and the workforce specialization to attempt something like this, and then attempts it. The Western engineering press mostly looked the other way, but the engineers didn't. Because China is already planning the next one. And somewhere, right now, there is a mountain that does not yet know what is coming. A site that looks unbuildable. A set of drawings that will be rejected once before someone signs their name to them. And a 38-month clock that is already ticking.